Welcome back, everyone. Today, we are untaking a truly fascinating journey. There is this wild statistic floating around, often cited as high as 80%, that an absolute staggering number of AI prototypes never actually make it into production. And the reason, scaling them up just introduces entirely new classes of failure that you don't see on day one. So today, we are going to look at the exact practical steps required to transition your AI agents from those neat little local prototypes running on your laptop into robust, highly scalable production systems. Think of this explainer as a masterclass in agent deployment. We're drawing directly from some incredible architectural insights on building intelligent workflows. So if you've been wondering how to actually scale up and ship these autonomous systems safely and effectively without hitting those common failure points, well, you are in exactly the right place. Our roadmap today covers 5 key architectural layers. 1. Strategies for consuming agents. 2. Containerizing with Docker. 3. Choosing your agent runtime. 4. Advanced multi-agent topologies. And 5. Security and governance. Okay, let's dive into this. Section 1. Strategies for consuming agents. Right, so our first critical step on the scale-up journey is all about strategy. Before you even think about spinning up servers or choosing a cloud hosting provider, you have to figure out how exactly your users or even your other internal systems will actually interact with the agent you've built. We call this consuming an agent. It's simply the architectural method by which an application, a user, or another system interacts with and utilizes the capabilities of that AI agent. But here is why this matters so deeply. How an agent is consumed fundamentally dictates how it must be deployed in the real world. Your deployment architecture literally always follows your user's experience. Think about it. If a user is chatting on a mobile app versus a backend cron job that's running nightly data summaries while everyone's asleep, the underlying plumbing absolutely cannot be the same. You have to build around the consumption method from the ground up. Let's look at the 3 basic deployment patterns for consuming agents. Starting on the far left, you'll see the embedded pattern. This is where the agent is baked right into the application itself. Maybe it's running directly in the user's browser, or it's tightly coupled within a single monolithic mobile application backend. Moving to the middle, we have the API pattern. Here, the agent is hosted independently as a backend service, and it's accessed over a standard web API, something like REST or GraphQL. The client simply sends a request, and the API returns the agent's response. Super standard. And finally, over on the right, we have a pure microservice setup. In this pattern, the agent is consumed essentially as a tool by other agents or by disparate backend services. They communicate over specialized protocols. We're talking about things like the open source Model Context Protocol, known as MCP, or Google's Agent-to-Agent Protocol, A2A. In this microservice environment, the agent doesn't even know what a human user is, right? It just receives structured tasks from the broader system and returns structured data. Now, obviously, each of these patterns comes with distinct trade-offs that you have to weigh really carefully. The embedded pattern is incredibly simple to set up. It's entirely self-contained, and it's absolutely fantastic for quick real-time responses because there's virtually no network overhead. However, it comes with some severe downsides. Mainly, it risks exposing your system prompts and core logic right to the client side, and it absolutely struggles with heavy, compute-intensive tasks. Then we have the API backend. This pattern separates concerns beautifully. Your front end handles the user interface, and your back end handles the heavy AI logic. This makes it exceptionally good for handling large documents and long-running retrieval augmented generation, or RAG tasks, mostly because the backend server actually has the memory and compute to process all that text. The catch? Well, if you want a real-time conversational feel, you're required to implement complex streaming support over the API, which definitely adds some engineering overhead. Finally, the microservice approach. This one is highly scalable and completely self-contained. It's literally perfect for asynchronous background work where thousands of agents might be operating in parallel. But it lacks a native user interface entirely. It is completely headless. So the crucial point is this. While embedding an agent might be the easiest way to start hacking on a weekend project, transitioning to APIs or microservices is absolutely required if you want to run complex, long-running processes like RAG tasks in a secure, enterprise-grade production environment. Moving right along to Section 2, Containerizing with Docker. Let's see how this builds into our next phase of maturity. Once we've decided on a microservice architecture, we really need to move from running code locally on our laptops to packaging it into isolated, deployable units. And for sure, that means containerizing with Docker. Taking an agent to production practically follows these 3 essential steps. First up, you generate your Dockerfile. A Dockerfile is essentially just a recipe that tells the system exactly what operating system dependencies, what libraries, and what code your agent needs to run. And here is a fantastic tip from the source material. Modern large language models can actually help you generate this initial Docker file just by looking at your app's code repository. You really don't have to write it all from scratch anymore. Second, you build the image.
This creates a completely immutable snapshot of your agent that will behave exactly the same way on your laptop as it will in a massive cloud data center. No surprises. And third, you orchestrate the deployment, basically bringing that immutable image to life as a running container.
Now that third step, orchestration, is where the magic literally happens. When you're building agentic systems, you almost never have just one piece of software running. This is where Docker Compose holds immense value for managing a microservices architecture. It allows developers to cleanly separate their concerns. Instead of manually launching half a dozen scripts in different terminal windows and crossing your fingers, you can stand up complex multi-agent stacks simultaneously. Imagine spinning up your React front-end UI, your Python background worker agents, a Redis cache for memory, a Postgres database for user state, and separate specialized tool services. The whole shebang, all with a single declarative command, Docker Compose up. It keeps your deployment incredibly clean, predictable, and highly manageable. You are essentially declaring the end state you want, and Docker Compose handles the networking, the volume mounting, and the startup order behind the scenes to make sure their entire agentic workflow comes online in perfect harmony. Section 3. Choosing your agent runtime. Now we pivot to what is perhaps the core technical decision you'll make in this entire process. Choosing your agent runtime and matching the deployment environment to the specific latency requirements of your system. I really want you to follow the logic on this flowchart because it is a total game changer for system design. It all starts at the very top with your target latency. Let's use a real-world example here. Say you are building a real-time voice customer service bot. Your user needs an instant response, meaning under 200 milliseconds, otherwise the conversation just feels laggy and totally unnatural. Well, according to the flow, if you need a response under 200 milliseconds, then you absolutely must target edge deployment, keeping the processing as close to the user as possible, like directly in the browser or on their mobile device. Now, what if you're building a more standard text-based chatbot? If your target response time is between 200 milliseconds and 2 seconds, then a standard API microservice hosted in the cloud is definitely your best bet. But let's say you're building a data mining research agent that needs to scour the internet, read 50 PDF financial reports, and synthesize a massive deep dive summary. That job is going to take much, much longer than 2 seconds. Maybe it takes 10 minutes. In that case, you cannot use a standard API because the web connection will simply time out on the user. You absolutely need an event-driven worker tied to a message queue. It's just a brilliant, straightforward way to route your architecture decisions based purely on how fast the system actually needs to reply. Let's contrast those extreme ends of the latency spectrum just to really solidify this concept. On the edge, you are relying on technologies like WebRTC or WebSockets for ultra-low latency bidirectional streaming. Because it's running right there on edge devices with limited memory and processing power, your tools need to be mostly stateless. On the other hand, an event-driven worker sits deep in your backend infrastructure and relies on robust message queues like Kafka or RabbitMQ. It is inherently asynchronous. When a user requests a deep research report, the request just goes into the queue. The worker picks it up whenever it has capacity, processes it for as long as it takes, and then drops the result back into another queue or a database. It completely expects high latency and handles it gracefully. And this brilliantly illustrates how conversational voice UI, which, needs to respond instantly to a spoken word, requires fundamentally different plumbing, infrastructure, and runtime environments than a background research agent that might spend 10 minutes thoughtfully reading and summarizing corporate documents. All right, Section 4, Advanced Multi-Agent Topologies. As we continue our scale-up journey, we're moving up the complexity ladder. A single agent operating in isolation is great for simple tasks, for sure, but true enterprise production systems usually involve multiple agents interacting in what we call a mature production topology. One of the absolute most effective setups is this front door agent pattern. Notice how the user at the top of the system only ever interacts with that single orchestration agent at the front door. This orchestrator acts a lot like a highly intelligent receptionist. It handles the initial interaction, uses semantic routing to figure out the user's exact intent, and then routes the complex tasks down to specialized, long-running worker agents sitting behind the scenes. It handles all this communication via an internal event hub or an internal API. The beauty of this topology is that the front door stays incredibly light, fast, and responsive to the user, while all the heavy lifting, deep thinking, and complex API tool calling gets pushed to the specialized workers in the back where it won't hold up the line. When you are managing multiple interconnected agents in a topology like this, your release engineering practices have to be absolutely ironclad. You cannot just push updates on a Friday afternoon and hope for the best. You need to promote changes through rigorous gates. You start with offline tests against static datasets. Then you move to shadow traffic, where you're actually mirroring real user requests to the new agent version without the actual user seeing the output, just to see how it behaves in the wild. Only then do you use canary releases, rolling it out to maybe 1% of your live users.
Furthermore, pending exact model versions like specifying GPT-4 0613 instead of just a generic GPT-4 tag, and pending exact tool versions is critical for consistency. And capturing rich, detailed execution traces using observability tools like Phoenix is absolutely non-negotiable. Think about it. If a multi-agent system hallucinates in production and accidentally orders 10,000 paperclips using your corporate credit card, you need that trace to debug exactly which agent in the topology failed, what specific prompt caused it, and why it made that bizarre decision. Without traces, you are literally flying blind. We also have to face a hard engineering truth here. In distributed systems, tools will inevitably fail. Networks will drop packets, third-party APIs will go down, and you will hit rate limits. It's just a fact of life. A robust multi-agent system must gracefully handle these harsh realities without crashing. You minimize failure points by building in comprehensive reliability patterns. This means implementing retries with exponential backoff. So if an API fails, the agent waits 1 second, then 2, then 4 before trying again, rather than aggressively spamming the server. You must define structured error returns using strict JSON schemas so that if a tool fails, the agent knows exactly how and why it failed and can logically adjust its strategy on the fly. You should provide fallback tools in case the primary data source is totally offline. And crucially, you must enforce strict execution timeouts. Without timeouts, a hanging web scraper tool could easily trap your agent in a runaway, never-ending loop, consuming compute resources infinitely until your servers just crash.
Which brings us to Section 5, Security and Governance. So we've arrived at our final and arguably most high-stakes phase of the scale-up journey. Once your multi-agent system is scaled, containerized, and running in production, how do you actually lock it down? How do you protect your sensitive data and prevent rogue actions? Now, what's really interesting about this slide is how simple but vital this core rule is. It's the principle of least privilege. In the context of AI, it means that agents acting on behalf of users should have the exact same limited access as the users themselves. Identity and access management, like OAuth scopes or database permissions, must flow directly from the authenticated human user down to the agent executing the task. Let's be real. If the human employee isn't allowed to access the HR payroll database or delete a specific cloud storage bucket, the agent acting on their behalf absolutely should not have the technical ability to do so either. You must never give an autonomous agent global admin access to your systems.
Let's deeply examine the specific threats these autonomous systems face out in the wild and the architectural defenses we use to neutralize them. Think about the sheer nightmare of stolen API keys and data exfiltration. If a malicious prompt injection convinces your agent to leak data, your defense here has to be strict sandboxing and egress control at the network level, ensuring the agent's container physically cannot send data to an unauthorized external IP address. What about the threat of a rogue tool execution, doing something terribly destructive, like dropping a production database table or firing off an angry email to a client? You counter that by strictly allow listing only the safest tools and enforcing mandatory human-in-the-loop, or HITL, checkpoints for any irreversible action. The agent can draft the email all at once, but a human must physically click send. Then there's the fascinating threat of agent collusion, where multiple agents in your topology actually reinforce each other's bad logic or hallucinations during a peer review step. You break that dangerous cycle by intentionally using entirely different underlying foundation models from different providers for your evaluator agents. For example, using an Anthropic Claude model to evaluate the output of an OpenAI GPT model ensures they don't share the same algorithmic blind spots. And finally, to protect against a runaway system trapped in an unbounded loop that burns through your entire monthly cloud budget in a single weekend, you absolutely must implement defense in depth by enforcing hard API rate limits and strict budget caps at the infrastructure level.
Making the jump from a local chatbot script running on your laptop to a fully scaled, secure, multi-agent architecture is incredibly exciting. It really is. But it brings immense power and, consequently, immense responsibility. You are building complex systems that can act autonomously on the real world. They're interacting with APIs, spending real money, and talking directly to your users. So I want to leave you with this provocative thought to mull over as you design your own platforms. As you continue to scale your systems and give your AI agents more and more autonomy, how will you guarantee they remain completely aligned to your business goals, absolutely secure from external threats, and always, always under your control? Mastering that delicate balance is truly the defining engineering challenge of this new era. Thanks so much for joining me on this explainer, and keep building responsibly.